Hi, we are beginning our part 2 of week 1, and we are looking at unsigned, meaning neither positive nor negative, binary arithmetic. So unsigned binary arithmetic. If we're going to add, let's just lay some ground rules on what this addition is going to mean to us. A 0 bit and a 0 bit in base 2 added together is going to be a 0. It's a 0 in both base 1 and base 10. That's what that line says. If I add a 0 and a 1 in base 2, I will get a 1. And in base 10, that's also a 1. Likewise, it's commutative if I go the other way. But here's where it gets a little tricky. If I add 1 and 1 in base 2, a 2 is represented as 1, 0 in base 2. And a 2, which we're real familiar with, is represented as this particular symbol here in base 10. If I add 1 and 1 and 1, that's going to be a 1, 1 in base 2. Now that is 1, 1 and 1, 2. That's what that represents. 1, 1 and 1, 2, just like we looked at earlier. And this would be a 3 in base 10. So now let's do a few of these. Let's look at this first one. I'm just going to add as I normally would, following these rules. 0 and 1, that is going to be a 1. 0 and 1, that's another 1. 0 and 0, that's a 0. 1 and 0, 1. That's what we get in base 2. Now let's look at this next one. 0 and 1, that's 1. Oh, 1 and 1, that's a 1, 0 in base 2. So I'm going to drop the 0, carry the 1, and now I add 1, 0, and 0, and that will be a 1. 0 and 1, that's 1, and then we get a 1. Okay, that one is finished. Watch this one, please. It's really fun. 1 and 1, that's a 0, carry the 1. 1 and 1, that's a 0, carry the 1. 1 and 1, that is a 0, carry the 1. And then 1 and 1. So this would end up being, let's see, there's the 1's place, that's the 4, that's the 8, that's the 16. So this would actually represent 32 in base 10. Well, that's fun. All right, so 1 and 1, that's a 0. Oh, this is your quiz question. Pop that in. I'm going to let you guys work on that one then. Might want to pause the video there and work it before I give you a confirmation of what it is. I end up getting a 5-bit number, and it is 1, 1, 1, 1, 0. Hopefully that's what you get to. If not, let me know. Come by and see me or email me. You can also do subtraction. We're not going to. We will do some multiplication though, but we're going to do it with repeated addition. All right, so we don't want to just look at just positive numbers. We have negative numbers, we have fractions. We want to look at everything. So we got to figure out how we're going to do this. I know that I only have bits, just 1 and a 0, and they have positions. So let's just say half the numbers are negative and half of them are positive. Okay. So I can see, like, with 3 bits, I have the 8 different things I can represent. That kind of cut it down because I could do, like, say -4, -3, -2, -1, 0, 1, 2. Ooh, I could only get to 3 that way. We could do it that way. Not what we're going to end up doing, but that's where we first start whenever we're like thinking of how we might want to do this. So we could do sign magnitude. Then we came up with another, and we'll look at that. And then we came up with another idea, and it was 1's complement. And then that had some problems. Sine's magnitude had problems, 1's complement had problems. Then we came up with this thing called 2's complement. That is what we actually use with our computers. And you will need to know 2's complement really well. Let's look at sine magnitude first. And you will need to know what sine magnitude is and why it has problems. So let's look at what it is first. We've already looked at the fact that 1, 0, 1 is a 5. Okay, and that means 1 in the 1's place, 1 in the 4's place. This is the 1's, 2's, 4's, 8, 16 place on a 5-bit. So if we let the first bit be the sine, then we only really have a 4-bit kind of situation going here. But I've got a 4 and a 1, and that adds up to 5. So we're going to say that that's a 5. All right? So to make it a negative 5, this was what, whenever we were first trying to figure out how to work with these bits and computers, we put this one out front, and we said, okay, now that's a negative 5. So if the first bit is a 1, it's negative. If the first bit is a 0, it's positive. Okay. So we can look here. Here's a 2 and a 1. That makes 3. That's positive. There's a 1 and a 0. That would be a 2. Since there's a 1 out front, that would be negative. Okay. We know what that is. Now, to get a negative number in 1's complement, what we're going to do is we're going to start with a positive number, and then that's going to be our representation of a positive number. I mean, we got 0 in the front. That's going to be a positive number in 1's complement. But to represent a negative number, you've got to flip all the bits. Okay, what the heck does that mean? So let's look at a 5. And we're going to use 5 bits, meaning that the first bit is my sine. Okay. 1's complement, that looks the same as what I've been doing. Let's see. If I want to make a negative 5, I need to flip the bits. Bam. That's it. Okay. So if I see a 1 out front and I'm in 1's complement, in order to figure out what that number is, just flip the bits. Now you get to play. So first off, what you're going to do is you're going to figure out what a positive 4 is, and you write that down. So I believe that would be 0, 0, 1, 0, 0. So you write down that. You say that equals a 4 in base 10. To get the negative 4, just flip all the bits. And that should get you your negative 4 in a 1's complement. So there's your next quiz question. Be sure you have your paper and pen out and get that written down. Here's our disadvantages, and you're going to have to answer this question on test, of course. In sine magnitude, you've got a doubling up here. For 5 bits, if all of them are 0, that's a 0. If you have a 1 out front, meaning that it's negative, oh, that's a 0 as well. And we don't want, it's going to cause difficulties down the road if I have 2 things representing, the representations being 2 different things. So we don't want that. 1's complement. Okay, I see in 1's complement, all zeros would be a 0, and then flip all those bits. Okay, that would be a 0 as well. That's pretty nice. But then our operations aren't simple. How do I add 2 and negative 3? This would mean that I would have to do different things. If I had 2 positive integers, I'd have to have another set of rules if I had 2 negative integers. And then if I had a positive and a negative, I'd have a whole other set of rules. And that is, I don't want to have different rules based on that. So a simpler scheme, which is not going to seem simpler at the front end, but it will be in the long run, and it is for the computer and our representations. A simpler scheme is 2's complement. Okay. 2's complement in base 2. This is what we're doing in order to simplify the circuits. And I'll just go ahead and let you know we haven't found it yet, but I'm going to let you know that this 0010, that's a positive 5. This 11011, that's a negative 5. Notice when I add these guys up, I get all zeros. I know that we have an initial carryover bit here, but we're going to learn that the carry bit doesn't matter because we're just looking at the 5 bits, because the carry won't matter. The carry has to be stored on another wire anyway. And if I have a positive 9, and here's a 2's complement, negative 9, and I add it, I also get 0. So that makes me happy because my operations work. So we do get the carry bit. It will be ignored because it requires a whole nother wire. All right, so here's some representations of 2's complement, just to look at them. These are our regular 0 through 7. Here is a 4-bit 2's complement representation of -1 all the way down to -8. Notice this -8. He is 1, so meaning that it's negative. All of these out here have a 1, and then all of these are zeros. That's really interesting. All right, so with n bits, I can go from 0 to 7, and then -8 to -1. And notice that all the positive numbers start with 0 and all the negative start with 1. All right, so here we go. This is how we're going to convert from binary, just straight up binary, to 2's complement. So we're going to write it as is with the number of bits that we've said. Then we're going to flip all the bits. That's the same as 1's complement. I got that. Oh, but 2's, you add 1 to the result. So let's look at an example. Let's look at 5. And then we'll look at the -5. So this tells me I write down my 5, which we did this last time. I flip the bits. I did that last time. And then I add 1. There is our representation of -5 in 2's complement base 2. So guess what I'm going to have you do next? Here's your next question. I want you to find the 2's complement using 5 bits of 4 and -4. Well, to find it for 4, it's pretty straightforward. 0, 0, 1, 0, 0. And that would be our positive 4. And follow this procedure to get your -4. Let me know if you have any troubles with it. And we'll move on. All right. If the lead bit is a 0, you go ahead and go to step 3. We're going to convert binary to decimal. If the lead bit is 1, that means it's negative, and I got to do something totally different. All right. So let's see. And if the original number was negative, then I'm going to add a sign. All right. So I'm looking at this number here. I see that the lead bit is a 0. I'm proceeding to step 3. I know that it's going to be a positive number, and so I have to just kind of organize where these guys are. So this 0, I'm just writing them all down underneath. I have 1 1s, no 2s, no 4s. Oh, I have an 8. There he is right there. I have no 16 and a 32 and a 64. Let me just pop those in. And there's my number written, and then I just like to add after that. I've got a 64, a 32, and an 8, and this number is 104 in base 10. So this big old long string of 1s and 0s is a 104 in base 10. Now the examples I'm using, I'm going to use 8-bit just so that we can be sure we know that we're starting in the same place here. So this is 8 bits. I count them out and I go, yep, the lead bit is a 1, so I know it's negative. Okay, so if the lead bit is a 1, take the 2's complement to get the positive number. All right. So the first thing I do, 2's complement for this thing So I'm going to flip all the bits and then add 1. So there's me flipping the bits. There's me adding 1. And now I have to look up here at the top and I go, okay, I've got a 1, I've got a 2, I've got an 8, and I've got a 32. So there they are. I've got 32, 8, 2, 1, and this number is then 43. Okay, so but I know that the original number, I still have to remember this, the original number was negative, so then I go, there's my final answer. All right. So next thing we have to do is it's your turn. So I want you to eight bits, 2's complement of all of these numbers. You'll want to put a pause on here because you are going to have to do a couple of these on tests. So I want to be sure that you know how to do this. The first thing that you had to do is say, oh, I've got a negative number. I've got a 1 out here in the front. That means I have to take the 2's complement of this thing. So I take the 2's complement, means I flip all the bits, and then I add 1. You should end up with 0, 0, 0, 1, 1, 0, 0, 1. That means that you've got to figure out now what that is in base 10. So I know I have a 1, 2, no, I have an 8, and I have a 16. And if you add those up, you should get a 26. When I have that 1 out front, I know that means it's negative. So you should end up with a negative 26 for that first one in base 10. Pause the video here and make sure that you have your work shown to show me that you can successfully do these problems for your quiz. I'll go ahead and give you your answers. I want you to make sure that you can do these because it's very important. All right, now we're going to go the other way. We're going to convert decimal to binary. There are many different ways to do this. I'm going to show you the method of subtracting powers of 2. So first off, just look at your number and go, where is he on this chart? You know, you have a decimal number. I want to convert the number 9 to binary, so I see that the highest power of 2 that'll go in there is this, 8. So what you're going to do is you're going to subtract the largest power of 2 that's equal to or less than 8 in our case is what we're looking at. And that is in the position 0, 1, 2, 3. So I might have one of those. I might have 1, 8. If I look at this 9, I can go, oh, I've got an 8 and I have a 1. If you're already thinking ahead, you might think 1, none of those, none of those, one of those, and you would be correct. But let's watch. 8's the highest power, so you take 9, so you put a 1 in that position, and then you'll do 9 minus your 8 because you just took one of those 8's out of there. And you keep subtracting your highest power of 2 until you get to the end. Well, 9 minus 8 is 1, so there's none of those, none of those. Oh, I got one of those. And now the result is 0. And so I can say, have one of those, put zeros in all the other spots. And that is how I will work these. So let's do a few more examples. These are all 8 bits. So we're going to find the 2's complement 8-bit for negative 9 decimal. All right, I've already done this in the previous slide, so I know that it's 1, 0, 0, 1. So I've got to use the 2's complement rules of representation. So I'm going to write it as 8 bits first. There's my 9 with 8 bits. I'm going to flip the bits, and I'm going to add 1, and that equals my negative 9. and my 2's complement base 2. Let's find the 2's complement for 104 as a decimal. Highest power 2 and subtract, so here we go. 104. Not quite this 7, but I see that 64 will go into it, so I know I'm going to have one of those. So I'll do 104 minus 64. I have 40 left. I have one of those that I've taken care of. Oh, I've got a 32. See, I have 32 still in there, so I'm going to do 40 minus 32. I'm going to put a 1 there. Now I've got an 8. I don't have any 16s in that, so there'll be a 0 there. But I know that I will have a 1 there for my 8, and then fill in all the rest with zeros. And 104 would look like as 8 bits. Remember, I have to write this in as 8 bits. So. Okay, question 2. Let's find the 2's complement for negative 85 as a decimal. This is a quiz question, so be sure and get out your piece of paper and start marking down. This is a quiz question. All right, let's see. First thing you've got to do is find out what 85 is as binary. So you're going to go through here and say, oop, I'm going to have a 64. And then you're going to subtract off, figure out what that is. Once you get the positive base 2 representation, remember that you will flip the bits, then add 1. At the end, you should get for your 8 bits 1 0 1 0 1 0 1 1. All right, and that's going to conclude part 2. I'll be making a part